These are the graduate students that were working on this project under Chris Proctor and Darren Rudnick. Chris does a lot of weed science work, but a lot of cover crop work, and Darren is irrigation. They were kind of focusing on the common site, soil health site. I guess if you guys have anything else you want to say, go ahead, but that's who these guys are, and we appreciate their work.
So a little bit brief about the research we're doing right now. So our research is kind of trying to compare the lab-based fertigation and sensor-based fertigation technologies with and without cover crops in the nitrogen leaching management process. And
clicker should work now. Hurry up.
so a little bit brief background information. Our research site is located on Convent Field, and the climate is about 25 inches precipitation per year, and the rain season is mainly in spring and early summer. And the main soil type is steamboat silt loam, and the groundwater source is from the Sandy Hill region. And from the irrigation water sampling results we collected in August 13th, the nitrogen concentration in the irrigation water is about 19.5 milligram per liter. And in our experiment setup, we have 3 levels of fertigation. One is lab-based fertigation, then deficit fertigation and sensor-based fertigation. For the deficit fertigation and sensor-based fertigation experiment setup, we all use the NDRE values to help us make the decision for the fertigation event. And for the lab-based fertigation, in the early of the season, we took some soil samples and sent it to a commercial lab and give them our targeted yield, and they give us their recommendation. And following their recommendation, we make our fertigation setup. And we have 3 types of cover crop setup. One is spring interseed. We have 20% winter wheat and 80% heritage. And another set of setup is fall interseed. So we have annual ray grass 20% and red clover 80%. And also we have one set of control plots. We didn't put any cover crops in those plots. And for each, so here is the main management summary and timeline for this growing season. So we have 1 starter to set rest, and we split the rest nitrogen fertigation, nitrogen recommendation into 2 fertigation events. And for the lab-based fertigation plots, we applied all of the nitrogen fertilizers into the field. And for the deficit and sensor-based plots, we only applied them once the sufficient index is below the threshold we set up, and the fertigation event will be triggered. So in this year, we fly the drone 1 day before each of the fertigation events, and we calculate the sufficient index for those deficit fertigation plots and sensor-based fertigation plots, and none of the plots was triggered the fertigation event. So there are like 60 pounds per acre difference between the sensor-based fertigation plots, deficit fertigation plots with the lab-based fertigation plots. And our main research objective, as we mentioned before, first we want to investigate the influence of different fertigation decisions with and without cover crop on nitrogen leaching. Also, we want to evaluate the cover crop potential to influence the nitrogen cycling. And our hypothesis is that the sensor-based fertigation could effectively reduce the nitrogen leaching in Bazile Watershed And the interseeding cover crop will reduce the nitrogen leaching in Bazile Watershed during the domain period. And some introduction about the sensors and equipment we use in the field. First of all, this is the UAV system we use. So every time when it's time for the fertigation event, we will fly the drone 1 day or 2 days ahead. And this drone will capture, will stop around like 300 photo points over the whole field. And it capture the set of photos, including the red lights, green light, blue light, near infrared, red edge, and thermal informations. And after we receive all the raw images, we will put it into a software named Pix40 Field. And this software will help us stitching all the images together and produce the maps for the whole field, so we can receive some field like RGB field map. And it could also help us calculate the vegetation index, such as the NBRE map, NBVI map, and this could also give us the thermal information of the whole plots. And we also have the information of each plot, and we put our map into this software. It could give us the average readings of each experiment plot for those NBRE values, NBVI values, and thermal values to help us make the decision for each plot. So another sensor we use in the field is the nitrogen leaching monitor equipment, the lysimeters. So this lysimeter is installed in the underground, and the bottom, as you can see on the image, like the black part is about 5 feet below the ground. It could capture all the depleting water, and it logs the infiltration water depth every 30 minutes. The infiltration water could be collected through the lysimeter as on this demonstrated image here. We collect the water sample from this part, and it could help us directly test how much nitrogen included in the deep percolation, and also it give us a very straightforward measurement of how much water leached through the whole soil profile. Unfortunately, this year we didn't capture any deep leaching. And another type of sensor we installed is AeroMark. So this sensor was installed in the middle of the field. It could give us some information about microclimates in the field, and also it could continually monitoring the plant growth status, and it gives us some vegetation index as well, such as the NBVI value, to help us kind of understand the plant growth status and help us make some irrigation decisions. And we also use 2 types of soil moisture sensors to help us monitor the water movement process. So the first type of sensor on left is called TBR 350, and it's we install it at 3 depths underground at 6-inch, 18-inch, and 30-inch. It's collected soil moisture data every 15 minutes. It could provide us a constant reading of the soil moisture. And another type of sensor on the right is the Newton gauge. So we collected the soil moisture data at 5 depths, 6-inch, 18-inch, 30-inch, 42-inch, and 54-inch below ground. And this type of sensor could give us a very precise soil moisture result.
My name is Victor. Before we jump to the cover crop part, I would like to just give a brief overview about cover crop, the benefits, which are many, as I pointed this slide here. So the first, the main benefit, the principal benefit that we are looking to this site that we are doing this project is to decrease nutrient leaching, which is our focus to decrease nitrate leaching on condom site. So in terms of nutrient scavenging, we have grass, which is grasses are focused on catching the nutrients from the ground for the profile. Also, we have the fixed nitrogen fix, which is legumes they play this role to fix nitrogen. Also, we have weed suppression. So some types of cover crops, they can decrease the weed suppression in the field. So, for example, cereal rye, they are pretty good on weed suppression, as an example here. Also, we have soil granular stability, which is an improvement of soil aggregate stability, which is pretty good as well in terms of water percolation and everything else. So those are there are many other benefits related with cover crop that cover crop has have. So, but I just point out here 4, which is our focus on condo site, which is our demo site. So cover crop is a challenge today, as we are hearing around. It's pretty challenging for every single farmer, grower, in terms of objectives. For example, if you want to plant a cover crop in your land, you have to establish first an objective first, your goal, and it's not the right time you're going to have the results. It's a little bit, for example, as I pointed here, at least 3 to 5 years to see any great result. So, for example, in terms of yield or soil health, at least 3 to 5 years to see any good result compared with your background, your field story. The other challenge is about seed costs. Depending on the seeds, depending on the cover crop you're going to plant in your land, some of the seeds can add an extra cost, can be expensive. If you look your whole budget, planting can be expensive as well. So if you're going to broadcast or interseed, that can be add an extra cost in your budget. Also, we have in terms of termination, you can use a roller crimper, can terminate using herbicides, which you're going to spend money buying herbicides, but those are those challenges, those 3 that I'm pointing out here as well. Also, as I said, each combination, if you're going to mix or if you're going to plant monoculture, there are challenges to establish some objectives for you. So if you pretend to, if you're planning to catch nitrogen from the soil, you have to choose the right cover crop, or if you're gonna fix nitrogen, you're gonna go towards to legume. So there are many combinations that you can do. So, but those are based on your objectives. Also, we have your current herbicide program. So if you, depending on your herbicide program, as a if you apply, depending on the herbicide you're applying there, you're gonna see some herbicides can leave in the ground some residual, and planting cover crop after that, you can notice some injuries in the cover crop and can impact your cover crop establishment as well. So jumping to our side, we interseeded cover crop when corn was V4 in June 16, and we did As interseeding, by that time, we did mix of grass and legume. On the grass side, we interseeded winter wheat, which is 20 pounds per acre. We did that based on the monoculture seeding rate. So the monoculture, if you're gonna plant winter wheat, full seeding rate would be 100 pounds per acre. On legumes, the legume side, we interseeded hairy veg. So as a 16 pounds per acre, which is 80% of the full rate, which would be 20 pounds per acre. So we mix this combination of grass and legume, and we interseeded as we are seeing here in this picture. Yeah. So in this picture here, the picture I think in the back I'm not seeing pretty well, but we have 2 rows. We interseeded between corn rows, so we interseeded 2 rows of cover crop. In this picture here, the picture is not a good quality for you guys in the back, but we have a very good establishment. I took this picture here when corn was V8. So you can see here this square frame here. This is a very good establishment for that time. We collected cover crop, we sampled cover crop separated. So we took 1 square feet, 1 square foot of frame, and we collected the biomass separated. So separated hairy veg from winter wheat, and we dried it for 4 days in a temperature of 140 Fahrenheit. After that, we waited and just to see to evaluate our dry biomass. We tried to collect another sample in October 26, but unfortunately we didn't find any cover crop there. So we are thinking that probably the canopy of the corn could avoid for the sunlight to reach the cover crop and permit the cover crop growth. Also, as I mentioned before, herbicide program could be impact at some point the establishment of the cover crop that we planted there. As I have in my mind right now, as a they've applied Acron Flexi and 2,4-D and Roundup. So probably the herbicide that was applied there caused at some point some effect. We noticed some. I could see, and the other guys that were working with me and Jamie, we saw some bleaching on those cover crop. So we could see some effect of their herbicide in those cover crop. Here it's possible, but the picture is so small, but we can see some bleaching the hairy veg here in those leaves. So the combination of lack of sunlight and herbicide residual, we had some problems and we couldn't find the cover crop in October. As I mentioned before, it's a challenge for us, so we are trying to figure out best combination, the best timing to plant, and also seeing the other factors as a herbicide and etc. This is our sample collection time. So we did soil sample deep nitrate sampling in 2020, November. 2021, we did another soil sample in June. So we evaluated soil health and nitrate. Also, we did cover crop biomass sampling, as I said, when corn was V8. We did leaf tissue sampling in August. Also, we did another leaf sampling in August as well. But the first one was corn was R3. The second sampling was the corn was R4. Again, we did another soil sample evaluating soil health and soil nitrate in August 17. We tried to collect the cover crop biomass in October, but as I said, unfortunately, we didn't find cover crop there. And we did the last soil sampling evaluating soil deep nitrate and also soil health in the beginning of December. So those are our results from soil sampling. This graph here, the first two columns here, the soil sample was conducted in June 10. This was prior to the second fertigation, second fertigation. So we can see here, treatment comparing treatment 3 and treatment 10, as we can see here in the table. Treatment 3 is the sensor fertigation plus interseeded cover crop, and treatment 10 is the late based fertigation, no cover crop. So in the top soil here, from 0 to 8 inches, the first 8 inches of the profile, we can see a very high amount of concentration of nitrate N. Just to remember, this ppm nitrate N is the nitrate available for a plant to use. From 8 to 36 inches, there are no difference between the concentration of nitrate N. But when we took a look in this chart here, the graph on the right side, it's a kind of many bars, but this is the whole treatment, all treatment that we have here. There are no difference between those. Just to remember, when corn reaches V6, V5, V6, corn start to take nitrogen from the soil, from the ground. So this was already R2, if I'm not wrong. So that's why it's pretty low, the concentration of nitrate N. But for me, one of the graphs that are very important to show here for you today is this graph. The green bar is the nitrate sampling that we did in 2020, November 2020. So we took an average across the plots, the treatments, 2020, and we compared with the treatments that we had last year, which are going to repeat again this year. But if you compare treatment 3, we have 3, 4, 9, and 10. Just, I don't know if in the back you can see, but treatment 3 is the sensor fertigation plus cover crop interseeded. Treatment 4 is the late-based fertigation plus cover crop interseeded. Treatment 9 is only sensor fertigation, and treatment 10 is late-based fertigation, no cover crop for 9 and 10. As we can see here, the treatment 10 across all the depths, it's on each foot. We have treatment 10 showing a very great amount of nitrogen, pounds of nitrogen per acre. This is in the y-axis here. We have pounds of nitrogen per acre. So treatment 10 show it for us a great amount of nitrogen, pounds of nitrogen per acre across the depths when we compare with even 2020 and even with treatment 3, which is sensor fertigation. But this graph here tells us the whole story. I think this is the perfect graph for us to compare both years. We have here, this is across the treatments, also across the depths here. So again, we have here in the y-axis pounds of nitrogen per acre, also across the depths here. The red line is 2020. The green line is 2021. So we had a slightly decrease of nitrogen free on on the soil across the depths, with the exception of the 4 foot. The difference here is pretty small, but the difference in average, the difference between those 2 years, 2020 and 2021, this graph is perfect to see that we had it was a very slightly decrease of nitrogen available, because we can assume that this nitrogen present in the soil there, it's we have greater chances to lose that for the watershed. So yeah, this is a very good graph.
So this is the result for our leaf tissue sampling at R3 and R4 growth stage. And we also applied the drone at the same time and received our NDRE readings. So from this plot, we can find that there's no significant difference among the treatments. So all the treatments seem to have similar growth status. And also we can find that those plots with a higher nitrogen concentration seems to have a higher NDRE readings. So we believe that the NDRE index is a very reliable vegetation index for us to make the fertigation decision and to help us understand how the nitrogen uptake process for the crops.
We are just showing here, since we didn't find any cover crop in October, we don't have any method to compare here, but this is only the biomass that we collected in this site. Yeah, I think the figure is a little bit distorted. I can't see it as well, the numbers, but pretty much we had a very good average of, for that time, since we interseeded cover crop before and we collected at V8. So we had it compared with other studies and the same rates that the other studies had as well. So we kind of had the same, almost the same establishment of cover crop, but unfortunately, we didn't have any cover crop to collect in October because of that points that I told you as a main cause to kill the cover crop that we interseeded. And also we didn't collect the cover crop that we interseeded in fall. So we're gonna evaluate, I think from now, a few days from now, to see the cover crop that we planted on fall last year. So I'm sorry for that. The picture is a little bit small. It's even hard for me to see here, but yeah, this is our cover crop that we collected in June last year.
So this is our yield results we collected from our targeted plots. So those bar graphs are the yield we received for the treatment and for each plot. I'm not sure if you can see it, but this dashed line with the purple points, those are the nitrogen inputs, the total nitrogen input we did this year. And those curves with the solid line and purple points, those are the total green uptake. Those are the total green uptake, actually total nitrogen uptake for the whole crop we collected for those plots. And funny story here is we find that the total nitrogen uptake for the crop is more than the total nitrogen input we did this year. So which kind of explain why we observed the decreasing in the nitrogen, decreasing in the soil nitrogen between year 2021 and year 2020. And also similar to the leaf tissue sampling, there's no significant treatment difference on the yield data among these targeted plots. This is also another good sign for us, uh, because even there's 60 pounds per acre difference on the nitrogen application, we still could receive a good result in those control sensor-based plots. And we also wondering, because we didn't receive any like deep percolation this year, we also wondering where did the water go. So we try to analyze all the soil moisture change throughout the whole season, because there are many plots and many treatments and there are many depths. So I plot them into different plots. So each row here means, so this row means is a comparison between treatment 2, 3, and 4. And the second row is a comparison between the treatment of 5, 6, and 7. And the bottom row is a comparison between the rest treatments. And each column here represents one of the depths with the soil moistures. And we can find that in the early growing season, the soil moisture have a similar response to our irrigations, and there's no significant increase in the deep soil moisture readings. And the last two column represents. However, after the 10, I think it's 10-inch precipitation on August 30, there is a significant increase in our last two depths. And we are wondering if this is a deep percolation because of the rainfall. But we didn't see any very significant increase in the meantime at the third depth. And based on our previous experience and also our constant reading from the TDR sensors, we believe this two significant increase is because of the rising groundwater table due to the recharge from the creek near our field. So that's kind of explain why we didn't receive any deep percolation in our limitations. And also we compared the total rainfall and our total cumulative evapotranspiration throughout the whole season. We can see that the water demand for the crop is about 600 millimeters for all the treatments, and our total water input plus our total irrigation plus our total precipitation is about 500 millimeters, which is still lower than the water demand from our crop. So that's kind of also help us explain like where the water goes. So the water was uptake by the plants. And so that's basically what we received from last year observation. And for this year, we plan to keep monitor the nitrogen leaching process, and we will increase our sampling process so we have a better tracking on what's happening in the field, and we can understand where the whole nitrogen movement process. And also, we plan to simulate the nitrogen cycling in a DNDC model, which could give us the nitrogen emission from the field, so we can have a better understanding of the total nitrogen cycling process. And also, hopefully we could apply the artificial intelligence in the analysis of UAV system to make it more accessible to further application. And that's all of our results here.